In part 1 of this video, I told you that a transistor is nothing more than a special kind of resistor. And I want to show you more of what a transistor can do and how it functions. But first, I want to do a little bit of review. Let's go back to Electronics 201. What is this circuit? This is a voltage divider. You got the input voltage in the upper left, going through a network of two resistors, and the output voltage on the right, coming out between the two resistors. And the voltage of Vout is proportional to Vin according to the ratio of the two resistors, R1 and R2. Here's the formula to determine that output voltage. Okay, output voltage equals lower resistor divided by the sum of the two resistors multiplied by the input voltage. As an example, I've put some values into my circuit and we'll calculate the actual output voltage with Vin as 10 volts, first resistor 100 ohms, second resistor 200 ohms. So let's calculate output voltage in this case. So output voltage equals 200 ohms divided by 100 plus 200, which is 300, times input voltage 10 volts. And 200 over 300 is 0.666, repeating of course, so we'll round that to 0.667 times 10 volts, and the output voltage is 6.67 volts. I know I'm boring you to death here. This will only take another couple of minutes. I want to show you a couple more examples of voltage divider calculations. Let's take a look at this. In this example, I've set the lower resistor R2 to a very low resistance value, 0.1 ohms in this case. So let's calculate what Vout would be in this case. In this case, output voltage equals 1/10 over 100 plus a tenth, which is 100 and 1/10, times 10 volts. Now, 0.1 over 100.1 is very close to zero. So close to zero that we might as well just say it's zero. So output voltage equals 0 times 10 volts. And Vout equals 0 volts. So in cases where the lower resistor is very small, like 0.1 ohms, Vout is going to be 0 volts. For a final example, let's change R2 to something very high, like say 10 million ohms, 10 mega ohms. So in this case the output voltage is 10 million divided by 100 plus 10 million, which is 10 million 100, times 10 volts. Well, 10 million divided by 10 million 100 is 0.99999, repeating of course. So let's just say it's approximately equal to 1. So output voltage equals 1 times 10 volts. So output voltage in this case would be 10 volts. So when we've got a voltage divider where the lower resistor is very high compared to the upper resistor, we can say that the output voltage is equal to the input voltage. Okay, so much for the review of second semester electronics. I just wanted to make sure that I'd covered the rules of a voltage divider, and they are 3. Basically, output voltage is proportional to the two resistances, and if the resistance on the bottom is low, output voltage will be 0. If the lower resistance is very high, output voltage will be equal to the input voltage. Okay, class, we've spent time reviewing some second semester electronics. Let's jump ahead a semester or two, and we'll talk about this circuit. What is this?
Well, Mr. Instructor, this is a Class A amplifier with an NPN transistor, and it's in the common emitter configuration, and its gain is...
No, 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 no! Stop. Step back. What is this circuit? This circuit is a voltage divider, where I have replaced the lower resistor with a transforming resistor, a resistor whose value changes a transistor. Even though this is a special case of a voltage divider, the basic voltage divider rules still apply. As the transistor starts with no signal on the base, the transistor's resistance is infinite. It is basically turned off, and V out equals the supply voltage. As we apply more base current to the transistor's resistance begins to fall, and the V out also begins to fall along with it, until finally base current has reached a maximum amount and the resistance across the transistor is 0, and V out will be at 0 volts. I shouldn't really say that we've applied maximum current to the base, because we could apply more current. That's not a problem. But the only thing is, by this time, the resistance across the transistor is 0, and it can't get any lower. So basically, V out is just going to stay at 0 volts. Let me show you graphically what I'm talking about here. In our graph here, the input is actually voltage applied to the base of the transistor, and the output voltage is measured at the collector. We raise the voltage a little at the base, and the transistor's resistance falls, which means the output voltage across the transistor also falls. Increasing the voltage at the base causes more of a resistant drop, and the output voltage drops further as well. We continue to increase the input voltage, but at some point the resistance across the transistor is going to fall to 0, and at that point the output voltage goes to 0 and can't get any lower. You can't have a resistance lower than 0 ohms, and the output voltage will stay at 0. Increasing the base input voltage will cause no further change in the output voltage. When the transistor's resistance is 0, we say that the transistor is saturated. It's in saturation. The circuit's output voltage is now distorted, clipped, due to saturation. Let's say at this point, our input voltage at the base begins to fall. At some point, depending on the transistor, the input will be low enough that the resistance of the transistor begins to rise as the transistor comes out of saturation. At this point, we see the output voltage at the collector begin to pick up again. However, if we keep decreasing the input voltage, at some point the transistor's resistance is going to climb so high that it will be pretty much infinite. At that point, it can't really get any higher. It's basically a broken wire at that point. And so the output voltage will equal VCC, the supply voltage. When the transistor is in this state, infinite resistance, we say that it is cut off. It's in cutoff state. It's turned off. We can decrease the input signal even further, even go into negative voltage if we want, but the transistor's resistance won't get any higher, so the output voltage remains as high as the supply voltage. This causes distortion again, more clipping, this time due to cutoff. Of course, if the input voltage rises again, the transistor will come out of cutoff, and the resistance will go lower, and the output voltage will start to fall. To get off on a sidetrack here, if we can arrange it so that the input signal at the base is high enough so that the transistor is not in cutoff, and still low enough that the transistor is not in saturation, then we can ensure that our output is going to be undistorted because the transition does not enter saturation and cutoff. This job is done by the two resistors on the left, R2 and R3. They're arranged as a voltage divider, and they add a certain amount of DC voltage to whatever input is coming through that capacitor. That capacitor is there, by the way, to protect the input from that DC voltage. This DC voltage will boost the input signal up into the transistor's so-called operating range so that the input voltage never goes below the cutoff, and it should never rise above into saturation. Adding an additional voltage like this is called biasing. We're biasing the input, and that makes it so that the output is clean. So here's our graph again, the base input versus emitter output. And it really shows why the transistor is so important. You've got a resistor here in a voltage divider network which will change based upon an input signal. And another cool thing about the transistor is a very tiny change in input voltage produces an enormous change in the transistor's resistance, so you get an enormous change in output voltage. And this is how the amplification occurs. It's just a side benefit of the transforming resistor. And as you can see, we've got a perfectly smooth output that is exactly proportional to the input. It's a transformation. So it's an exact transformation. Wait, what's that? The phase is inverted? Oh, cry me a river. Give me a break here. Okay, fine. You want the input and the output to be in phase? Well, tell you what I'm going to do. I'll just redesign my circuit a little bit so that it has a gain of 10, because I'm going to use a slightly weaker transistor. And then I'll build another amplifier circuit just like it right next to it and feed the output of the first to the input of the second. So now I've got a two-stage amplifier with a total gain of 100, and because the phase changes twice, the total output phase is in phase with the input. How you like me now? Okay, sorry about that. Didn't mean to blow up on you there. But let's go back to the basic that I wanted to share with you, which is, yes, even though this is a common emitter Class A amplifier with an NPN transistor, it essentially is nothing but a voltage divider where a resistor has been replaced with a transistor. This transistor's resistance changes as the signal at the base changes, and you end up with the output voltage proportional to the input signal, input voltage in this case. And it's just that simple. Now, for a more complicated example, let me show you this. Wow! What have we here? Well, this is the schematic for an op-amp, operational amplifier. An op-amp is just one tiny amplifier on one chip, but it has a gain that is so high it can be considered infinite. That's right, infinite gain. And it's very complicated, as you can see. On the far left, you've got your input. It goes through an initial amplifier called a difference amp. Don't worry how that works. But the input is amplified twice. It gets passed through that capacitor in the center to a couple of stages of power amplifier, which amplifies it enormously. And the final output is on the right. And like I say, this is really complicated and everything. And if you want to delve into some of the innards of it, you can go to the Wikipedia page just like I did, which is where I got this picture from initially. But what is this? What is this mess? Well, except for the capacitor in the middle, everything you see here is a resistor of some type. Either a classic passive resistor or a transistor, a resistor whose value changes. So this entire mess is nothing but a very large and complicated voltage divider. And what are the three rules of our voltage divider? The output is proportional to the input. The output is never lower than the 0 volts, and it's never higher than the supply voltage. Actually, I should change that because this particular op-amp can have two supply voltages, a positive and negative, like plus 12 and minus 12. But the rule is still basically the same. The output voltage can never get above plus 12 volts or below minus 12 volts or whatever it is you're using. So even though we say, yes, this has infinite gain, it doesn't mean that if you put a microvolt on the input, you're going to get 10 billion volts output. No. All it is a voltage divider, so your output is either going to be positive supply voltage or 0, or negative supply voltage or whatever you're using. Now, what good is a circuit where it's always in saturation or cut off unless you have the very tiniest of input signals? We'll leave that for another day. In part A of this video, I showed you that a transistor is nothing more than a resistor whose value changes based upon input signal. And these examples should show you how you can use that variable resistor in an actual real-world application. And I hope this helps you, and I hope you've enjoyed this video. Thank you.